Hi everybody, and welcome back to Digital Integrated Circuits. This is the second section of Lecture 5, Technology Scaling. In the first section, we discussed Moore's Law. We'll now be going into scaling models. So at the end of the first section, we discussed the goals of technology scaling. If we scale a technology by 30%, then we get a double of the reduction of the size or the area of the device, of the transistor, and then we can put twice as many devices on a chip, and that's how we can keep up Moore's Law. Well, this guy over here, Robert Dennard, who was a fellow at IBM, who actually invented DRAM, he wrote a groundbreaking paper in 1974 where he described the MOS scaling principles that accompanied us for almost 40 years. So what he saw or noticed was that as long as we scale all the dimension of a MOSFET by the same amount, which we call S, we will arrive at better devices and lower cost. So what we can see here in the illustration is different dimensions that we're going to scale. Particularly in our high-level model, we're going to take the length of the transistor and scale it by S. So the length is going to go from L to L divided by S. The width of the transistor, which we can see here, is going to go from W to W over S. The oxide thickness, which is actually not shown on this, is going to be from Tox. We're going to divide it into Tox by S. The doping of the diffusions is going to grow by S. So from Na, we're going to go S times Na. And VDD, we're also going to reduce by S, as well as VT. Okay. To see how our model is going to work, I just want to remind us of our simple timing and power models that we discussed before. The unified model for MOS transistor conduction we wrote down like this. The drain to source current is something called K transconductance by VGT, that's VGS minus VT, times something we called VDS effective minus half VDS effective square times the channel length modulation effect. Okay, VDS effective, we said, is the minimum of VGT, VDS, and VDSat, which sets if we're in saturation, velocity saturation, or linear operation. And when we take this K here, the transconductance, we said that K is the mobility times the oxide capacitance times the width of the transistor divided by its length. This oxide capacitance over here, it's the permittivity of the oxide divided by the thickness of the oxide. We also can go and look deeper into that and say what our on current is. Our on current is basically our transconductance K times VGT squared if we're in saturation. That's like a saturation current. Okay, so that's when we are in saturation, that's what we get. It's actually Kn over 2, but it doesn't matter because it's proportional to Kn. Okay, we get our on resistance. On resistance of the transistor could be, if we're taking our D and our S and we have VDS, which equals to VDD on it, then we can see that if this is IDS, okay, what we get is that the equivalent resistance R on equals VDD divided by I on. And I on we wrote down here. Okay, the TPD, the propagation delay, well, if we have a capacitor over here and we're loading the capacitor through our transistor, I guess this would be a PMOS in this case, and this would be S, and this would be D, but it doesn't really matter. Okay, then we have our R on times the C out, and if we're connected to some other type of a transistor here, then that would be CG in our model. Okay, so TPD, we write it's proportional at least to R on times CG. Then dynamic power will be the frequency of operation times the capacitance times VDD squared. So I have the dimensions that we said that we're going to scale over here. We write them in S to the minus 1 instead of 1 over S. It kind of helps. Okay, and we have different properties here in this table. So we'll start with the oxide capacitance. Oxide capacitance is Cox, and we said that the oxide capacitance is equal to the permittivity divided by the thickness. The thickness, we said, scales by S, so we get 1 over S, and that comes out S. And is that good or not good? Well, we don't know yet. The device area. So the device area A is basically the width times the length. And both the width and the length were scaled by S. So we get S to the minus 1 times S to the minus 1. It brings us a total of 1 divided by S squared, and that's really good. That means we got exactly our square reduction in device size or in area. Gate capacitance. Another thing that we want to make smaller is the gate capacitance, because that's going to be costing us power. So the gate capacitance is Cox times W times L, or times A. And we said that, again, the Cox over here, we saw that it grows by S, while W times L reduces by S. So altogether, we get a reduction by S, and we want to reduce the gate capacitance. So again, that's another good feature. How about transconductance, Kn? We want to have as much transconductance as possible, because that's basically the gain of our transistor. Okay, so here we have mu n Cox times W over L. And when we put the way that they scale, mu n doesn't scale. Cox scales by S, W and L both scale by S to the minus 1. We're left with S, so our transconductance grew by a factor of S, which is really good. How about our saturation current? Our saturation current, we said, is Kn VGT squared. Well, if we have Kn, which we showed before, grew by S, and VGT squared, we know that VDD, as we said, reduces by S, and VT reduces by S. This pretty much reduces by S as well. So S times 1 over S squared gives us 1 over S. That doesn't seem so good that we have a lower saturation current, but let's see how it affects us. Well, our on resistance, we said, is VDD over ion. VDD reduces by S, and ion, we said, also reduces by S. So having them both reduced by S means that our output resistance, it actually, or our on resistance, it stays constant. So let's see how that affects our intrinsic delay. Our intrinsic delay is proportional to R on CG. Well, we have CG up here reduces by 1 over S, and our R on, we said, stays constant. So we get a total reduction of 1 over S, and having a lower TPD means that we're going to be able to raise our frequency basically by S, so we're very happy with that. Next, we have power. So power, we said, is FC VDD squared. If we can take our TPD and lower it by S, then we can raise our frequency by S. Our C is going to be our C gate, and our VDD squared is going to be 1 over S squared. It gives us a total reduction of S squared in the power, and that's really great. So how about power density? That's something we haven't discussed until now, but when we take a transistor and we operate it, the fact that we can put more transistors on the chip means that we're going to be, even though they have lower energy, they may be, the more transistors are going to be making more energy, and that will dissipate more heat. So we actually should look at the number of, the amount of energy that we dissipate per size. So that's the power density, or the average power divided by the area of the transistor. Well, the average power we see is 1 over S squared, and we saw that the area is 1 over S squared. So it gives us a constant power density, and a constant power density means that we can use the previous heat dissipation options, such as packages and cooling and so forth, and they will still work across scaling generations, across technology generations. So what we see here is this rare case of a win-win situation where everything done in this scaling model, which is this full Dennard scaling or constant field scaling, it gives us benefits in everything from area through power and speed. What about when we put in a short channel transistor? So for short channel, we actually saw that we have this model of the velocity saturation where VD sat, we saw that it equals the critical field, which is basically constant over processes, times L. L scales to 1 over S, so VD sat also scales to 1 over S. And then we change our saturation current now. It's going to be Kn VD sat times VGT minus VD sat. So again, Kn is going to grow by S as we saw before. VD sat is going to go down by S as we saw now. VGT, we saw also VD and VT go down by S, as does VD sat. So this pretty much also reduces by S. So we're going to get a total of 1 over S, and actually nothing changes when we look at full Dennard scaling with short channel transistors. So the last slide showed us the principle that has led to scaling for the last 50 years. Okay, assume that we scale our process by 30% every generation. So 1 over S equals 0.7. That's a 30% reduction every scaling generation. That means that S is equal to the square root of 2. Okay, therefore, if the area scales by 1 over S squared, we get a reduction of 1 of a half. Or the die size goes down by 2x every generation, which is what we want. Corollarily, we can put twice as many devices on the same size die. In addition, we saw that the speed goes up by 30% because we had an increase or a decrease of TPD by S. And the power also gets cut in half without any increase in power density. So we have one of those rare win-win free lunch situations, and whoever has a strong stomach can read this little cartoon that I loved. But what happens if we want more speed? We saw that TPD is basically RC, or CG, times VDD over I-on. We can aggressively increase the speed by keeping the voltage constant. Why does that work? Since I-on is proportional to K VGT squared, and that is proportional to S, that means that TPD is proportional to S to the minus 1, which is CG, times 1 over S, which is VDD, times 1, divided, which we said if we don't scale VDD, divided by S, which is I-on, and so we get a total reduction of S squared in TPD, and that's really good. We get an extra benefit of speed. Okay, and this led to the fixed voltage scaling model, which was used until the 90s. And so, in other words, we tried to keep our voltages constant at somewhere around 5 volts. And you can see here that the technology voltage, it stayed pretty constant over many different technology generations. However, at some point, it started going down. Now, there's another benefit for keeping our technology voltage constant. It's not only that we get this greediness and extra speed, but it also is that we can keep the voltages between different products to be standard. So if we know that our VDD over many technology generations is going to stay 5 volts, for example, then we can take chips that were made in different technology generations. They all work at 5 volts, and they can talk to each other within a 5-volt interface. Now that we have different chips running at different voltages, we have to have level shifters and all kinds of things in between them to enable them to speak to each other. So this led to Moore's law in frequency, and we see this exponential scale in transistors per chip over here, and we also see that for a while there was a real hard exponent going up in frequency, and at some point it evened out kind of to what the rise in transistors per chip was, but in the early 2000s this flattened out completely. Okay, so that's kind of interesting. What we saw in our model here is that we could get this increase in speed by either fixed voltage scaling or even with Dennard scaling. But over here we saw that it actually panned out completely. And we can see the same thing over here happen. So the transistor keeps rising. This is a bit newer graph, okay? And the frequency, again, rose exponentially. But at some point in the mid-2000s, it just panned off and went straight, and same with single thread performance. Something interesting we can see here is that the number of cores actually started to grow. The number of cores was 1 for a long time, and that we'll see in a second why. But instead of actually increasing the power and increasing the frequency, we started increasing the number of cores instead. So let's see what happens if we go over to a fixed voltage scaling model. And now we again changed our VDD. So instead of being at 1 over S, it's at 1. Everything else up to this point stays the same. Okay. So, but now that we have our VDD at 1, we go down to our P average. And what happens with our P average? So first of all, our intrinsic delay, as we saw before, it goes down to the squared. So that's really good because we get a much higher increase in speed. However, when we look at the power, we have FC VDD squared, and now F is S squared because it's 1 over the TPD, right? C is S to the minus 1, and VDD doesn't scale, so it stays at 1. That means that our power now actually increases by S, and that's not too good. Okay, but when we look at our power density, we have a huge problem. So our power density is P average divided by A, the area, and the area is scaled by 1 over S squared. So that means what we get actually is a rise to the third. We get a cubic rise in the power density, and that's something that's intolerable. When we look at short channel, it's even worse. So what happens with the velocity saturated devices? So again, our I-on is Kn VDSat times VGT minus VDSat, something like that. Okay, and that means that I-on actually stays pretty much constant because remember, VDSat also scales at 1 over S. So the on current doesn't increase, and this leads to less effective speed increase. Again, this is a very high level model. It's not completely accurate, but it shows that we don't get as much gain in speed as we got with a long channel device when we keep the voltage constant. So we see that TPD only goes down by S and not by S squared. However, when we look at the power density, it still increases quadratically, and this is a big problem. And it actually led to what we call the power density crisis. So at ISSCC, which is the main conference for chip design, for chips in general, the solid state circuits flagship conference, Patrick Gelsinger from Intel stood on the podium and showed something like this plot. And at the plot, he showed that over here in the mid-90s, we reached on the surface of the chip, due to power density, we reached basically the heat of a hot plate. So if you'd put your finger on a chip without a fan on it, you'd really burn your finger. But keeping on and rising the power density, we'd actually, if we continued after the Pentium 4, which was already really power hungry, we were going to reach the heat of a nuclear reactor, which is crazy. And rising even further in the towards 2008 or so, we would have reached the heat of a rocket nozzle on the chip, which of course would have burned the chip. And in fact, there are some plots that show reaching the temperature of the sun up here sometime sooner. So this could not continue. This was a big shock to everyone, and everyone who saw it figured that we couldn't keep on raising our frequency as we had up till that time of the Pentium 4, which actually could run at like over 3, maybe 4 gigahertz, and this is a long time ago. So there's this nice video, pretty old, but it shows what was going on. It's from Tom's Hardware, and let's see what happens when we remove the CPU fan. Okay, so we were going to take a few different cores we had here. So here's a Pentium 4 2000. We're going to remove the fan, and playing this game that was really popular at the time, Quake, it goes a little slower. Okay, and we measure the temperature, and it's still running, and it's kind of lagging a bit, but at some point it starts to really slow down. Okay, so you see you can't really play, but once we stick the fan back on and the heatsink, you see that we continue playing regularly. Okay, temperature didn't get that hard, but the application slowed down, and nothing actually happened with the CPU. When we take an Intel Pentium 3 1000, let's see what happens when we remove the fan playing Quake. Okay, you see, very soon everything just freezes. Really, the application just froze. Okay, the CPU again survived, but the application totally froze up. AMD, which actually hit a lot of problems in the Athlons about that time, they really had a heat density problem. So let's see what happened. Took off the thing, immediately we get this kind of blue screen of death, total failure, and there the CPU starts to burn out. And it really burns out our whole chip and ruins everything. And that's because of this rise in power density. It just burns out the chip. Now if we look at the temperature measurements, you see that this already reached 360 or 370 degrees. So that was really, really hot on-chip temperature. Okay, and the CPU and the board go up in smoke. We can see similar things with other CPUs, but I think we can continue at this point. Okay, so that was a real crisis. It was a wall that was hit, and that's why what we can see that we had to discuss what happens with power. So this is power. This is not power density, but you see that there was a power trend that power rose from the early times of like the 4004 until we reached like the 286 or so, somewhere around here. There was a very hard drop in power, and that was mainly because of things like going over to CMOS technology and so forth. But then this increase, this Moore's law of frequency, caused the power to really increase heavily in all the processors that we had throughout the 90s. We were doubling our speed every processor that we bought, and they just got really, really hard to cool, and we had to have these huge heat sinks, and it just got pretty crazy. And that's why what happened over here is after Patrick Gelsinger's talk at ISSCC and so forth, we started to make dual cores, then quad cores, octa cores, and so forth, and spread, parallelize our computation in order to get similar throughput at lower frequencies. So Just to summarize the technology scaling models, fixed voltage scaling, which was used from the 70s until the 90s, it means that we keep the supply voltage constant, and this had two benefits. On the one hand, it kept all the devices with the same supply voltage, which was really nice. We could have one battery on our board that powered all the chips without all kinds of regulators, but it also gave us this huge boost in speed. In this case, only device dimensions are scaled. The problem was that it causes the power density to rise incredibly. Full Dennard scaling, which is what Dennard showed that could work over a long time, it keeps a constant electric field on everything. And there we have to scale both the device dimensions and the voltage by the same factor S. And with the electric field staying constant, we eliminate breakdowns and many secondary effects. And this was what was used from the 90s until the mid-2000s. However, what happened was that really we had to start playing around with all kinds of physical phenomena and so forth and keep the power in hand. And so we started to scale device dimensions by S and the voltage by U. Another big problem, and one of the reasons that we had to change, is the leakage power. So when we looked at leakage before, we saw that the off current is exponentially dependent on the threshold voltage, Vt. Okay, so I off is either the power of minus Vt divided by n Vt. Okay, in the case of full scaling, the leakage current increases exponentially as Vt is decreased. So the minute we get to a low enough Vt, then every time we change Vt by 1 over S, we're going to have an exponential increase in this off current. Well, again, when the minus Vt is large enough, because Vt is large, the off current is still negligible. But once it gets small, this off current becomes very substantial. In fact, since the 90 nanometer node, static power is one of the major problems in ICs. You can see here this plot that shows the normalized power. We had static power, which was really nothing until the mid-90s, versus dynamic power, which was much higher. And at some point, somewhere around that time, where you see that we petered off and stopped this general scaling model, this like kind of full scaling model, is where we have, for certain chips, obviously this is really dependent on the application, the static power overcame dynamic power. This is also often called dark silicon, where you may have cores that are resting, or memories, or something that's not working right now, but it's still leaking a lot of power away.